All right, so in Chapter 8, Section 5, we're going to be talking about probability. So we are going to be generalizing the type of probability that you've probably seen before, which is discrete probability, to applications of probability using integration and the idea of area. So for a discrete random variable, we define the probability of an event A. So the probability of the event A occurring are the number of ways A can happen divided by the total number of events in a sample space. So in example 1, we have if an urn contains 3 red, 4 green, and 5 blue marbles, what's the probability of drawing a red marble? Well, we can look at the number of ways that we can draw a red marble. So since there are 3 red marbles, there's going to be 3 ways to draw a red. And then the total number of events in the sample space is going to be, well, if I reach in there, I'm going to draw a marble. So there's 3 red, 4 green, and 5 blue, which is 12, right? So then the probability of me drawing a red marble is going to be equal to the number of red marbles divided by the total. So 3/12 or 1/4. So it would appear that we would have a 25% chance. And if you think about it, that makes sense, right? We have 12 marbles in this container. We have 3 red, we have 4 green, and we have 5 blue, right? So if we visualize it this way, the part to the whole, so 3/12, right? It's the same idea. So that's the idea of our discrete probabilities. So not all random variables are going to be discrete. So we're not always going to be drawing marbles out of an urn or something like that. So for example, what is the probability that a light bulb lasts over 800 hours? This is an example of what's called a continuous random variable because its values range over an interval of real numbers. Every continuous random variable has a probability density function. So if f of x is a probability density function, then the following things must be true. F of x has to be greater than or equal to 0 for all x. That means that the probability of an event happening, the smallest it can be, is 0, right? You can't have negative probabilities. That doesn't make sense. An event can have 0 probability, which means it's impossible, but all events must be greater than or equal to 0. The second quantification is that the sum over all events has to equal to 1. To make a connection to what we were talking about up here, we have the probability of drawing a red was 1/4. What would have been the probability of drawing a green? Well, there's 4 green, and how many was our total? 12. So green's going to be 4/12. And what's the probability of drawing a blue? There were 5, so 5/12. I'll write this back in its form this way. If we were to add up all of these probabilities, what would we get? Well, what's 3/12 plus 4/12 plus 5/12? Well, 3 plus 4 plus 5 is 12/12, and what do we get? 1. So the probability of the entire sample space has to be 1. So the probability of an event happening is 1, which means some event will always occur. If I reach into that urn, I'm always going to draw a ball. if that's my intent, right? So the same thing holds, but we're now generalizing it to our continuous random variables. So we say that the integral, which is going to represent the sum over all events in our probability space, has to be 1. So this means that the probability that x lies between a and b can be found by integrating between a and b. So the probability that the random variable x is between a and b is the integral from a to b of f of x. So let's come back up here. And draw a picture once again. So I did this, but I'm going to draw an improved picture. So let's draw I'm going to make our marbles rectangles because it'll make my math that I'm doing easier. So if we do this, there's our 3 red, our 4 green, and our 5 blue. So if we interpret this now in terms of an area diagram, that dude's supposed to be blue. And then we have our reds. We have something that looks like this. So what would be the area of this rectangle if each of these squares had side length 1? So the total area would be 4 by 3, right? So that's going to be 12. Then what would be the area of the red? Oh, that's the 3 that we have here over our total area. 12 is 3 twelfths. What's the area of the green? 4. Our whole is 12, and so forth. So this idea of changing probabilities into areas follows from the idea of discrete probability. So it shouldn't surprise us that an integral should be able to do the same work for things that are continuous. All right, let's take a look at example number 2. So if f of x is the probability density function of a light bulb that lasts x hours, write the integral that represents the following probabilities. So the light bulb lasts between 100 and 300 hours. So we want the probability that our random variable x is in between 100 and 300 hours. So then these are going to be our limits of integration. So we would integrate from 100 to 300 of f of x dx. And that would be the probability that the light bulb lasted between 100 and 300 hours. All right. Part B asks, well, what would be the probability that the light bulb lasts less than 700 hours? Well, since time can't be negative, what would our lower limit of integration have to be? 0, right? Is less than or equal to x, and we want this less than or equal to 700. So we would want the probability that this is less than 700. So note, we can actually get rid of this, and we'll see why a little bit later. It's not wrong, and you would get the same answer, but we're going to see some examples of probability density functions, and when we are off the quote-unquote domain that makes sense, we just make them equal to 0. So since a light bulb can't go backwards in time, the probability of something happening back there is 0. So then if you add up the area under the zero curve, you don't get anything, right? So I would accept either one, but be a little careful. WebAssign's going to want it more like this, right? But they mean the same thing mathematically because the density function is going to be 0 below 0 anyway. All right. Let's take a look at our next couple. So let's take a look at C, because it asks a very interesting question. And this is one of the key differences between discrete probabilities and continuous probabilities. So we want to know, well, what is the probability that a light bulb lasts exactly 65 hours? So if we just proceed, we want the probability that x is exactly the same as 65. Well, we need to write that as an inequality, right? So if we go back in our time machine to Calc 1, we learned about a wonderful theorem called the Squeeze Theorem, right? The Squeeze Theorem told us if something is greater than or equal to 65, but it's also less than or equal to 65, what does it have to be equal to? Well, let's draw a picture. So if I'm at 65, and if I shade everything to the right, it has to be greater than or equal to 65, but then it also has to be less than or equal to 65. Where's the and? What's the only point that's in the and? 65, right? Because if you're greater than or equal to 65 and less than or equal to 65, that set contains exactly one point, and that one point is 65. So that would be 65 is less than or equal to x is less than or equal to 65. So as an integral, it would be the integral from 65 to 65 of f of x dx. Well, what's the value of that integral going to be? No matter what f is. 0, right? Because the width of our interval is 0. Doesn't matter what f is. So the probability that the light bulb lasts exactly 65 hours is 0. I know that seems a little counterintuitive because we don't think of time as a continuous event. Like when I look at the clock right now, I would tell you that it's 1:43 in the afternoon. But that's not true, right? It's 1:43, some fractional seconds, some fractional on forever and ever and ever, right? There's always something going on. That's the thing about continuous probability distributions. It's like the idea, if I tried to pick a number, a real number between 0 and 1, well, what's the probability of me picking any one real number? Well, how many of them are there? An uncountable infinity, right? It could be like 0.364794118, blah, blah, blah. Just keep spouting off decimals forever. I wouldn't even have to stop, and it would stay between 0 and 1, right? So what's the probability that I pick that exact infinitely long string? Pretty close to 0. In fact, it is 0. So we have to be a little bit careful because certain things don't generalize well from discrete probabilities to continuous probabilities. So if we have an interval like this that has no width, the probability has to be 0. All right. Lastly, what would be our integral for the light bulb lasts longer than 300 hours? Well, that's the probability that, or 800 hours. I said 300, but it's 800 hours. So that's the probability that x is greater than or equal to 800. Well, that would be the integral. It's got to be bigger than 800. Well, how far up does x go? Forever. So what's our symbol for forever in math? That would be infinity, right? So we would integrate from 800 to positive infinity of f of x dx. And that would represent the probability that the light bulb lasts more than 800 hours. All right. So when we're using integrals to calculate probabilities, We really need to think about the probabilities as a set on the number line, or an interval, and then discover that appropriate interval, and that gives us our limits of integration. Those intervals can be infinite, like we saw in some of them, and that's okay. All right, so now we want to take a look at this probability density function. Or perchance an alleged probability density function. So determine if this is a probability density function. So what were our requirements for something to be a probability density function? So we had two things, right? F of x always has to be greater than or equal to 0. And if we integrate from negative infinity to positive infinity, what should we get out as our value? 1. All right. So we want to determine if this is a probability density function. So we have a piecewise defined function. It is equal to 0 for all x values less than 1. It's equal to 1 over x for x between 1 and e. And then once we get to e, its value once again drops to 0, right? So if we were to draw a sketch of this graph, so that's 1. We have our interval here is 1, over here is e. We have our graph is equal to 0 for all x less than 1. So it's on the x-axis. It gets to here, it has a hole. And then at 1, it jumps up to 1 over 1 is 1. And then it's going to be that part of the hyperbola, the 1 over x graph that looks like this. And out here at e, we're going to be at 1 over e. So it looks like, I made it look like a straight line. And that's really not the case. It looks like this. And then at e, it drops back down and goes to this, right? So we have a function that looks kind of like this, and it's only non-zero between the values of 1 and e. So this is what I was alluding to earlier in the light bulb situation, where we would say it can't be less than 0. So on this interval right here, so from negative infinity to 1, what's the value of that integral going to be? 0. And on the interval from e to positive infinity, what's the value of our integral going to be? 0, right? So our integral here is equal to 0, and our integral here is equal to 0. It's only non-zero for the values between 1 and e. So if we were to integrate from negative infinity to infinity of f of x dx, formally we would have the following. We would break it up into 3 integrals. We would have the integral from negative infinity to 0 of f of x, negative infinity to 1. And on that interval, from negative infinity to 1, we get that the integrand is 0, right? So we would have 0 dx plus the integral from 1 to e, and that's on this chunk in the middle, right? We would get the integral of 1 over x dx, and then on the interval after that, we would have e to positive infinity. So that would be this piece, and we would end up with, once again, 0 dx. So as we surmised from the picture, if my integrand is 0, the value of this integral is 0. The value of that integral is 0. So then our integral from negative infinity to infinity of f of x dx is really just the integral from negative infinity to infinity, or, sorry, from 1 to e of 1 over x dx. So now we can actually do that integral. So what's the antiderivative of 1 over x? ln absolute x. And we integrate that from 1 to e. So that gives us the natural log of e minus the natural log of 1. The natural log of e is 1. The natural log of 1 is 0. And we get 1 minus 0. And we get 1. So the value of the integral from negative infinity to infinity of f of x dx is indeed equal to 1. Okay, so that's our first part. Well, I think that was technically the second part. So the first part was we need to determine if it's always greater than or equal to 0. Well, 1 over x's domain is from 1 to e. 1 to e is positive, so a positive divided by a positive is positive. So yes, our graph is always, or our outputs of our function are always greater than or equal to 0. So yes, this is a probability density function. All right. So a couple of things that are worth noting in this. So a function that looks like this, that is equal to 0 from negative infinity to some number and from some number to positive infinity, is said to have compact support. So what that means is that outside of some bounded interval, the function is equal to 0. Right? So in this one, our bounded interval is really small. It's just between 1 to e. But as long as it's finite, we'll always be able to do these integrals fairly easily. We can do them when it's infinite, because we know how to evaluate improper integrals. They tend to make things a little more complicated, but they can be done. So we like these types of functions because they're a little bit easier to work with. But as we'll see in some other examples, they won't always have this nice compact support. All right. All right, so let's go ahead and take a look at this. So what will our limits of integration be? So what are we going to be integrating in between? Yeah, 0 to 5. So we're going to have the integral from 0 to 5 of c times x squared dx, and we want this to equal to 1. And we're going to solve for our value of c. Well, c is a constant, so we just pull it out of the integral. And we need to integrate x squared, so we're going to get x cubed over 3. And then we evaluate that from 0 to 5, and that still needs to be equal to 1. So we're going to have c times 5 cubed over 3 minus c times 0 cubed over 3 is equal to 1. Well, 0 cubed is just going to be 0. So 5 cubed is 125, so we get 125c over 3 is equal to 1. So we divide both sides by 125 over 3. And that's going to give us c is equal to, well, we multiply by the reciprocal, so we're just multiplying by 1. We get c is 3 over 125. So that would be the value of c that we would need in order to make that a probability density function. All right. So, exponential decay probability function. So from pre-calculus, we know that an exponential decay function has the form f of t equals a times e to the negative ct for some constants a and c. We will restrict the domain to t greater than or equal to 0 to find a relationship between a and c. So we're going to do pretty much the same thing you guys just did, but now instead of going from negative infinity to infinity, we're going to be using the interval t greater than or equal to 0. So we're going to have the integral from 0 to positive infinity of a times e to the negative ct dt, and we want this to equal to 1, right? So that's what it means to be a probability density function. So when we pull our a out of the integral like we did before, so from 0 to infinity of e to the negative ct dt, we take our antiderivative. So what is the antiderivative of e to the negative ct? So negative 1 over c e to the negative ct, and we're going to evaluate that from 0 to infinity equals 1. And this is the result of a u substitution, right? Because if I let u equal negative ct, then du is equal to negative c dt. So divide by negative c, and I get dt is equal to negative du over c. So then our integral would become e to the u times dt, which is negative du over c, so then we would get negative 1 over c, the integral of e to the u. And then what's the integral of e to the u? E to the u, and we plug it back in and we get our negative 1 over c, e to the negative ct, right? Okay, so we evaluate our integral. So we have negative a over c times e to the negative infinity is going to be 0 minus e to the 0 is 1. And we want this to equal 1. So negative ac times negative 1 is positive ac is equal to 1. So multiplying both sides by c, we get that a has to equal to the number c, right? So for this to be a probability density function, a and c have to be the same number. So substituting that back in, we get f of x equals c e to the negative ct dt. And I wrote f of x. And of course it's f of t. So the next thing we want to talk about is the mean or the average of the probability density function. So the mean of a probability density function, mu, is equal to the integral over the entire probability space, so from negative infinity to positive infinity, of x times f of x dx. So note, this is the same as the x-coordinate of the centroid of the region bounded by the curves f and the x-axis, right? So the mean, or the average, or the center of mass, or whatever we want to call it, is really what we think it is, right? So when we're finding it, we multiply our probability density function by x and integrate to find the centroid, or the center of, or the moment, and then it turns out that it's also the centroid, and that comes from the fact that we have here. So in our previous section, x bar was equal to my divided by the mass, right? Well, using that same thing, we have the x bar is equal to the integral from negative infinity to positive infinity of x f of x dx divided by the integral from negative infinity to positive infinity of f of x dx. But since it's a probability density function, what do we know the value of the integral has to be? 1. So because it is a probability density function. So then putting all of that together, dividing by 1 doesn't change anything. So x bar is the integral from negative infinity to positive infinity of x times f of x dx, and we'll call that mu. So x bar and mu are really the same thing for probability functions anyway. All right. So for example number 4, we're asked to find the mean of the exponential distribution f of x equals c times e to the negative cx for t bigger than 0. So as we just discovered, that's our exponential decay distribution, right? We solve for a being the same as c. And we want to find the mean of this distribution. So our mean, mu, is equal to the integral from negative infinity to infinity of x, f of x, dx, or in this case, it really should be t's. I had that incorrectly here. That should be a t. So t, f of t, dt. So filling in those values, we're only non-zero for positive t values. So that's the integral from 0 to infinity of t times c e to the negative ct dt. So we need to evaluate this integral. So once again, cleaning it up a little bit, we have the constant c, which we don't know, so we'll pull that out of our integral. So c times the integral from 0 to infinity of t e to the negative ct dt. So how are we going to do this integral? Well, it's by parts once and then one more integral, or we just tabular the thing, right? So we can either by parts or tabular. Tabular works out nicely. So e to the negative ct. So the derivative of t is 1, and the derivative of 1 is 0. So then we get negative 1 over c e to the negative ct, 1 over c squared e to the negative ct. And then we make every other term negative, and we connect our diagonals. So we get that our antiderivative is, so let's not forget this guy. So we have c times our antiderivative, which is negative t over c e to the negative ct minus 1 over c squared e to the negative ct. And then we need to evaluate that from 0 to infinity. So when we go to infinity, we're going to get 0, because e to the negative infinity is going to be 0. And we know in a race that exponentials always beat polynomials. If you're not convinced, we could write it as such. So if we take the limit as t goes to infinity, and we have t e to the negative ct, we can just put the constant out in front. We don't care. Well, this is infinity times 0, so we need to massage it a little bit and move our exponential down into the denominator, making its exponent positive. So now, as t goes to infinity, I get infinity divided by infinity. So then this is type infinity over infinity. So we have our indeterminate form. So by L'Hopital's rule, we take the derivative of both the numerator and denominator. So the derivative of t is going to be 1, and the derivative of e to the ct is c e to the ct. But now when I take the limit, I have a constant over infinity, and a constant divided by infinity is going to be 0. So I mentioned that exponentials always beat polynomials, and this is why. Even if I had t to the 100th power, what would I do? L'Hopital's rule 100 times, and I'd have some giant number, which would eventually be a constant, divided by an exponential. Because what's the derivative of e to the ct always going to be? E to the ct times a constant. You can never differentiate an exponential away, but a polynomial will always differentiate away each time its degree goes down, right? So it doesn't matter even if it's a degree a million, eventually, a million derivatives later, you would have a constant, right? So exponentials beat polynomials in a race 100% of the time. So for both of these, on our first part, we get, don't forget our c. So at infinity, we have 0, or negative 0 minus 0, and then minus our lower limits of integration. When I put 0 in for t, I get negative 0 over c e to the 0 minus 1 over c squared e to the 0. Putting 0 in. So then a whole bunch of things are 0, and I've got about a billion minus signs. So plus and plus. We multiply our c's in. So we end up with c divided by c squared times e to the 0 is 1. So we get 1 over c. So this gives us that mu is equal to 1 over c. All right. So before we do the next example, we need a couple of facts. So for an exponential distribution, we have what we just found, mu is equal to 1 over c, or solving that equation for c, c is equal to 1 over mu, right? Where mu is the mean or the average for that distribution, right? So when we're talking about measures of central tendency, there's usually three that we talk about. The mean, which is one of the averages, the one that in common speech we call the average and the mean are the same thing. We have two others. One's called the median and one is called the mode. So when we're talking about the median in statistics, what are we talking about? So the median is the value that divides the data set in half. So what that means is if we have a data set, it's the number that's in the middle out of all of our data set points. So if we look at all of them, it tells us, well, 50% of the data set is above that value and 50% of the data set is below that value. So it's basically saying, well, however this data is spread out, we find the one that's in the middle, and we have our upper 50% and our lower 50%. So they often cut that in half again, and you'll hear things in terms of quartiles and things like that, but this isn't a stats class. But the median is just the line that we use to cut it in half. All right. We're going to need these two things to talk about our next example. So suppose the waiting time for a customer's call to be answered by a company's representative can be modeled by an exponential distribution, and the average wait time is 5 minutes. A, find the probability that a call is answered during the first 5 minutes. B, find the probability that a customer waits more than 5 minutes. And C, find the median waiting time. That is, find M such that M, the integral from m to infinity, equals f of x dx. We'll talk a little bit more about that one as well. So using these facts, we know from our previous work that our exponential distribution looks like this. F of t equals c e to the negative c. But we also know that c is equal to 1 over mu, right? And mu is what again? The average or the mean. So let's put all of this together. So if we know that the average wait time is 5 minutes, that tells us that mu is equal to 5. So going through our chain of equalities that we have there, we have f of t is equal to the integral from 0 to infinity of c e to the negative c t dt, but we also know that c is equal to 1 over mu e to the negative 1 over mu times t dt, Or for this problem, sorry, I just shouldn't have the integral yet. It should just be this guy. Because we're just talking about our function. So finally, f of t would then be equal to 1 over mu, but mu in this case is 5. So 1/5 e to the negative t over 5, right? We just substituted in our value of mu, which was 5 for all of that. So when we have an exponential distribution and we're given the average or the mean, we can substitute that in to get our probability density function, right? And we already did all the legwork setting up the relationship between A and C, the relationship between C and mu, so we don't have to verify that this integral is equal to 1. If you did it, it would give you 1. But that's all good to go because we've done all that work and proven that it had to be regardless of what the numbers mu were or anything else. Okay, so we want to find the probability that the call is answered in the first 5 minutes. So that's the probability that the call is between 0 and 5, right? Because you can't answer the call before they called. So that wouldn't make any sense, right? So you can't have negative time. And we want it to be less than 5 minutes. So then this is going to be the integral from 0 to 5 of 1/5 e to the negative t over 5 dt. So we can pull our constant out in front. So the integral from 0 to 5 of e to the negative t over 5 dt. So what's our antiderivative of e to the negative t over 5? If you don't remember, we'll just do our u substitution. So let's let u equal negative t over 5. Then du is equal to negative 1/5 dt. So solving for dt, dt is equal to negative 5 du. Since we have limits of integration, let's go ahead and switch our limits of integration. So u of 0 is going to equal to negative 0 over 5. Did that backwards. 0. So we're going to get 0. And u of 5 is going to be negative 5 over 5. So that's going to give us, negative 1, right? Okay, so now our new integral becomes the integral, so our 1/5 comes along for the ride. Our new lower limit of integration is 0. Our upper limit of integration is negative 1. We have e raised to the u. And our dt is the same as negative 5 du. So our positive 1/5 and our negative 5 are going to reduce out to give us negative 1. The integral from 0 to negative 1 of e to the u du. And when we have a negative, we can just reverse our limits of integration and change our sign from negative to positive. So this is equivalent to the integral from negative 1 to 0 of e to the u du. So e to the u's antiderivative is e to the u. From negative 1 to 0 is e to the 0 is 1 minus e to the negative 1. So 1 minus 1 over e, We could get a common denominator. I don't think it really makes it any simpler. E minus 1 over E. Regardless, we can get our probability now by putting that into our calculator. So alpha y equals, we have E take away 1 all over E. We hit enter, and it looks like the probability of the call being answered in less than 5 minutes, if the average wait time is 5 minutes, is 63.2%. All right, so that's part A. Part B says find the probability that a customer waits more than 5 minutes. How are we going to calculate this? So for part B, we want the probability that they wait more than 5 minutes. So x, or t, is greater than or equal to 5. I think I put x's earlier too. No, I didn't. That's good. So t is greater than or equal to 5. So that's going to be the integral from 5 to positive infinity of our same thing. So I'll pull my 1/5 out in front, e to the negative t over 5 dt. So this integral is going to go down pretty much the same way as the last one, right? But we just have to change our limits of integration again. So we make our same u sub. U is going to be negative t over 5, and du is going to be negative 1/5 dt. So dt is negative 5 du. And then changing our limits of integration, u of 5 is still going to be 1, so negative 5 over 5 gives us negative 1. And u of infinity, well, negative infinity divided by 5 is going to be negative infinity, right? Because infinity divided by a constant is infinity. So subbing all of our stuff out, we get 1/5 times the integral from negative 1 to negative infinity of e to the u times negative 5 du, which is going to give us the same thing we had before, the negative of the integral from negative 1 to negative infinity of e to the u du. And once again, we can reverse it. So from negative infinity to positive 1 of e to the u du. So we evaluate, our antiderivative is e to the u, and we evaluate from negative infinity to 1. So that's e to the 1 minus e to the negative infinity is 0. Yes, sir. All right, so I'd had a typo. It was negative 1 up here, not positive 1. I flipped it over. It didn't change. So this should be negative 1, which makes this negative 1, which gives us 1 over e, which is the right thing. So I was approaching the number positive e, and I know that can't be the case because e is bigger than 1. Probabilities can't be bigger than 1, right? So we get 1 over e for our probability. And if we do 1 divided by e, we get this value. So it looks like the probability that they wait longer than 5 minutes is going to be approximately equal to 36.8% rounding, right? So we didn't actually have to do that integral. Let's draw a picture and see about why. It doesn't have to be super accurate, but we know we're integrating from t equals 0 all the way out to infinity, right? And we have some curve that looks like this, right? Well, when we integrated from 0 to 5, the integral from 0 to 5 of our probability density function, we got 0.632 or e minus 1 over e, right? So we got this area right here was the decimal 0.632. The second thing we were trying to find, so let's call this A1. The second thing we were trying to find was this area that went on forever. And what did we call it? Let's call it A2. Well, what do we know about A1 plus A2? What does it have to equal? Well, A1 plus A2 is all of the area underneath a probability density function. So since f was a probability density function, A1 plus A2 has to be 1. Because f is a probability density function. So when we found that A1 was equal to e minus 1 over e, and then we needed to find A2, which was the other set, equals 1, we could have just minus e minus 1 over e. I really should put that minus sign down here. Minus e minus 1 over e gives us that A2 then had to equal to 1 minus e minus 1 over e. So then getting our common denominator by multiplying the top and the bottom by e, we get e minus e minus 1 all over e, which gives us e minus e plus 1 over e. And the e's reduce out, and we get 1 over e. Oh, that was exactly the value we got for that integral, right? So the reason that worked is our first integral went from 0 to 5. The second integral went from 5 to infinity. Both of those integrals together have to be 1, because that's the definition of a probability density function. So if you know one of them, the other one is 1 minus whatever the first one was. It's called finding the complement of the event. And that's true for all kinds of probabilities. And sometimes it's easier to find probabilities that way by using complements than directly trying to calculate them. All right, the last one is we want to find the median waiting time. So what we really want is we want this to be equal to 50%. And what's 50% as a decimal? 0.5, right? Because we want to find the value of m such that half of the probability space is on either side of this line, right? So we're going to do our integral from m to infinity. What else could we do? Based on what we just talked about, what does that integral have to be equal to? The integral from 0 to m of f of x dx has to equal the integral from m to infinity of f of x dx. And they both have to be 0.5, right? Because they're complements of each other. Because if I find one of them is 0.5, what does the other one have to be? 0.5, right? So we're going to have either one of these. So let's do our integral from 0 to, oh sorry, let's do the m to infinity. Doesn't really matter. Put our 1/5 out in front. E to the negative t over 5 dt. And we want this to be 0.5. So let's get rid of that 5 by multiplying both sides by 5. So then we just have the integral from m to infinity of e to the negative t over 5 dt is equal to 5 times 0.5 is 2.5. So now we do our antiderivative, and we've done this one quite a few times. So it's going to be negative 5e to the negative t over 5. And we need to evaluate that from m to infinity. We got that antiderivative because you always divide by whatever the constant is. Our constant is negative 1/5. So e divided by negative 1/5, we take the reciprocal, it becomes negative 5. We did the u sub in the previous two. It's the same thing. You'll get the same answer regardless of how you do it. And this needs to equal to 2.5. So we have negative 5 times e to the negative infinity is 0 minus e to the negative m over 5 is equal to 2.5. So now distributing, we get 5e to the negative m over 5 equals 2.5. So we divide by 5, we divide by 5, and we get e to the negative m over 5 is equal to 2.5 divided by 5 is 0.5, but I'm going to write it as a half, because 0.5 and a half are the same thing. Solving for m, we take our natural logarithm of both sides. And that gives us negative m over 5 is equal to the natural logarithm of 1/2. And by log properties, so our quotient property, the natural log of 1/2 is the same as the natural log of 1 minus the natural log of 2. The natural log of 1 is 0. So we end up with negative m over 5 is equal to the negative natural log of 2. So once again, we're going to multiply both sides by negative 5. And that gives us m is equal to positive 5 times the natural logarithm of 2. Five times the natural logarithm of 2, and we get 3.465, so 3.47-ish. So that tells us that 50% of the people will wait less than 3.47 minutes. 50% of them will wait longer than 3.5 minutes, approximately, right? So the last thing we want to talk about is the normal distribution. So in statistics, if you've taken a stats class, this is exactly the probability density function that they use to make the z-score table. When you look up z-scores, you are actually finding the area underneath this probability density function. That's what a z-score is. They've just normalized it and then made a table because most people in stats haven't learned integrals yet. So we look them up in a table instead of doing an actual integral. All right, so a random variable is normally distributed if it can be modeled by a normal distribution. The density function is 1 over sigma square root of 2 pi e raised to the negative x minus mu squared over sigma. where mu is the mean and sigma is the standard deviation. So the base probability density function is e to the negative x squared. And it does not have an elementary antiderivative. So the density function for the normal distribution has to be integrated using numerical methods. So Simpson's rule, midpoint rule, trapezoid, whatever. But it does not have an antiderivative and it can't be calculated directly. That's just the way that it is.